Okay, so welcome everyone to week 4 live session of NPTEL Digital Circuit course. I am Om Maheshwari and today we will solve some questions which will help you in your assignment as well as in your exams. In this week, mainly we will be solving some questions based on uh, logic gates as well as a little bit introduction to arithmetic circuits and some combinational functions also. Let us start. So let's start with some simple questions first. So the question is the Boolean expression a bar b plus a b bar plus ab is equivalent to. Please try it out once and let me know your answers in the chat or you can open to my also. Do we have an answer for this question? Are you able to solve it? Okay, can anyone let me know if I am audible? Okay. Jen says a plus b. Anybody else got any answer? Okay, so Satika Jen has correct answer. So let us see how we do this one. So we have a bar b plus a b bar plus ab, right? And what we can do is let's take a bar b plus let's take a common. This is b bar plus b. This will become 1. So we have a plus a bar b, and this is a plus b. This is an identity, right? If you remember, a plus b bar e, a plus a bar b is a plus b. So our answer is a plus b. Anusha, is there a doubt? Screen is not visible. Uh, is it the same case with everyone? Can anyone else tell me if the screen is visible?
It's visible.
Okay, thank you. Anusha, can you maybe reconnect? I think there's some problem at your end. So, anyone else has any doubt in this question? Okay, great. So, let's move on to the next one. Which of the following is the simplified form of the Boolean expression x plus y into x plus z? Please try this one next. Okay, so we again have the answer. Question is x plus y, x plus z. If you multiply these, you will get x plus xz plus xy plus yz. Take x common. 1 plus z plus y plus yz. This gives you, this whole thing will be 1 x plus yz. Okay, so let us move on to the next one then. I think we'll go through these initial questions first. So the question is the combinational circuit implementation of the following Boolean function is what? So you have been given these midterms. You have to identify the circuit which this represents. So how you will do this? You will start with the K-map to identify what we are talking about. Function of A, B, and C. So A bar A, C bar, B bar C, B C, and B C bar. Right? It is 0, 1, 2, 3, 4, 5, 6, and 7. We have one at 1, 2, 4, and 7. If you see, when we have these alternate ones between at the in KNAP in these position, it usually is XOR gate. So you can even write it. Sorry, A bar D bar C plus A bar B C bar plus A B bar C bar plus A B C. This is actually this function is A XOR B XOR C. So the corresponding answer is A. Okay, so next one is when the set of input data to an even parity generator is 0, 1, 1, 1, the output will be 1. So even parity generator means you want to have even number of ones, right? Generate even number of ones. But in this number you have 0, 1, 1, there are odd number of ones. So A parity generator will generate another one to make it even, right? So yeah, your answer would be 1. Suppose your number was 0011, then a parity bit would have been 0, still even. Then your answer would have been 0. So your answer in this case is, let's forget it. The answer in this case is 1. Is this clear? Is there a doubt in this question? Okay. So the next question is, the input to a logic gate A is 1100 and B is 1010. What would be the output if the logic gate is NAND gate? Please try this out once. Okay, so let us see this. Well, this is a very simple question. I'm equal to, let's say, AB bar 0011011. Your NAND gate output is 0 here. For all the cases, it is 1. So your inputs are A equal to 1, 1, 0 and 0. B is 1, 0, 1, 0. So output Y can be, when A and B both are 1, the output at the NAND gate is 0, will be 0. And in the other cases, whenever any of the inputs are 0, your output is always 1 in NAND. So here we have, in any other cases there are 0, so output will always be 1. So the answer will be 0, 1, 1, 1. B option. Right. All right. So next question. The number of inputs and outputs in a half adder circuit are. Simple question again. So in a half adder circuit, if you remember, the half adder circuit is something like this. So this is can, correct? So these are two inputs, these are two outputs. Whereas this is half adder. Whereas in full adder, let me draw just the block diagram. If A, B as well as carry in. here sum and carry out. This is full add. It has three inputs and two outputs. Our answer here is 2 and 2. Okay, next one. The output Y in the circuit below is 1. When? So, if to try this out, what is the condition when you will always get Y equal to 1? Do we have any answer? Okay, so let us solve this one. So to find out when this will be 1, we need to find what is the Boolean expression of Y. So let us solve this circuit. So here we have all the NAND gates. So here input is P and Q. So our NAND output will be PQ bar. Here you have Q and R. Here will be QR bar. Here it is R and P. Output will be PR bar. Right? So here it is, these two are again landed here. So your output will be PQ bar dot QR bar 4 bar. Right? And this is just a shorted NAND gate is equivalent to a NOT gate, or also a shorted NOR gate. All are NOT gate. So this is NOT gate. So here your output will be PQ bar dot QR. This bar will get removed when we do a NOT gate. Okay, so your input here is PR bar. Now again we have to do NAND of these two inputs. So your output Y will be PQ bar dot QR bar dot PR bar whole bar, right? And we can use De Morgan's here. PQ plus QR plus PR. This will be PQ plus QR plus PR, right? So this is Y. So your Y will be equal to 1 when either PQ equal to 1 or QR equals to 1 or PR equals to 1. So when any of the three inputs, any two out of three inputs are 1, then your output will be 1. So your answer will be option B. Two or more of the inputs PQR are 1. Is it clear? Okay. So let us move on. There are no doubts here. Okay. So this is a theoretical question. So you must have seen in the videos. Dynamic hazard is a, so we have three types of hazards, right? We have static and dynamic. Static, we also have static 0. We have static 1. Static 0 hazard is when your output is supposed to be 0, but somehow you get in some portion you get a 1. Static 1 is your output is supposed to be 1, but in some portion you get a 0, right? It is in the name, right? Static 0. It should have been statically 0, but you get some some discrepancy. Similarly, in static 1, your output should have been 1 as a static, but you get some discrepancy in some portion. In dynamic, you can have multiple transitions like these. Like it is supposed to be 0, but it goes to 1, then 0, then 1, then 0, something like that, then goes to 0. Dynamic, you may have multiple transitions. So why do these happen? These happen due to delays in circuit. And those delays in general, what do they cause? They cause, so these usually happen in those circuits where in the Boolean expression you have a variable, let's say A and A bar, both when both are present in your Boolean expression, then there is a chance that these hazards could be there, right? So we can associate like this hazard happens when uh, A plus A bar in this case, sorry, happens when it is A bar, A plus A bar. So what does this mean? Why I have written this and this? So A and A bar, these are always equal to 0, and A plus A bar is always equal to 1. But if there is some discrepancy in this, like instead of 0, there is 1. So maybe like you have some gates, let's say A, so you have an AND gate, you have a NOT gate, so A bar, right? So due to delay of this NOT gate, the waveform you get is not directly flat. It has some, in some portion it goes to 1 and then goes to 0. Right? It could happen. Let's say if A was this, it went from 1 to 0. A bar was 0, but due to some delay of the NOT gate, it went to 1 here. opposite maybe. Just a minute. Okay. Let's say this A goes from 0 to 1, and A bar goes from 1 to 0, but due with some delay. There's a delay due to not gate. Then our output, let's say this Y will be 0 till here. Then with some delay of this AND gate, it will be 1 here, then go 0 again, right? This here static 0 hazard. Due to this delay in this time period, both are 1, right? But it could never be the case. A and A bar ideally should, when A is 0, A bar will always be 1, or when A is 1, A bar will always be 0. But in this portion, due to delay, A and A bar both are 1. That's why we get a small portion where output is also 1. Output is simply A bar becomes 1 here, which is the cause of this delay. Similarly, in case for static 1, your this is A, we have a NOT gate, this is an OR gate, A bar, right? So let's say your A goes from 1 to 0, A bar goes from 0 to 1 with some delay of the NOT gate again. Your output Y will be 1 1, it is OR gate, right? So whenever any of them is 1, it will be 1, but due to this delay, it will be 0 in this portion. In this portion, both are 0. With some delay, you will get 0 here. So this is static 1 hazard, which is associated with A plus A bar, right? You are doing A plus A bar here. So whenever in expression you are getting A plus A bar, there is a chance of static 1 hazard. Whenever you are getting A and A bar, this A and A bar, right? There is a chance of static 0 hazard. And dynamic is simply a combination of both. That's why you get these multiple on and off. So in dynamic, you have, and write it as A bar plus A. Whenever you have these kind of variable expressions, you can have a dynamic hazard. Okay, so the question was, so we will use all this information in the coming questions. I hope this is clear. So the point was, are these expressions clear? Why we are taking these expressions for static, dynamic, and everything? So whenever you have, let's say, any Boolean function, f equals to a plus b plus c, a plus b bar plus c. So here, if you see, when let's say a equals to 1 and c equals to 1, then your f will become b bar, right? This can cause the condition a equals to 1 and c equals to 1 can cause a static 0 hazard. Sorry, it should not be 1, it should be 0. Alright, so whenever you have A equals to 0 and C equals to 0, there is a chance in your circuit that because when A equal to 0 and C equal to 0, your expression becomes B bar. And if there is some delay in generating B and B bar, then you will have a static 0 hazard, which we just discussed here, right? Like A and A bar, with due to this delay of NOT gate, you get a false one here. Okay, so are these clear? Can anyone confirm these expressions? Or do you want me to repeat them? Okay, nobody's saying anything. So I suppose it is clear. If you have any doubts, you may please ask. So let us get back to the question. Dynamic hazard problems occurs in both combinational and sequential circuits. So your answer would be C. You can have these cases in both combinational and sequential circuit, right? So your answer C is correct. Thank you, Neeta. Okay, so let us move on. So I just introduced this because we will be using this information in some future questions. So just small things to remember. So the next question is an interesting one. In the figure shown, the output Y required is AB plus C bar D bar. What are the gates G1 and G2? You will want it to be AB plus C bar D bar. What will be G1 and G2? Yeah. So let us see this. This is an OR gate. You have there Q bar, B bar. Here you have C plus D whole bar, which is effectively equal to C bar dot D bar. Right? So this one component you already have here. So this gate must be an OR gate. Right? From here, then you want AB. So how do you get, if your inputs are A bar and B bar, how do you get AB? Right? So if we do A bar plus B bar whole bar, it will give me A bar dot B bar, which is AB. Right? So this gate must be NOR gate. So the answer is NOR and OR. Okay, so if there is no doubt, let us move on to the next one. What is the primary cause of glitches in digital circuits? This is theoretical question, so let us not waste much time here. Primary cause of glitches is the delays, right? We just saw due to delays between, say, some variable and their inversions, we get glitches or hazards. Option B. Glitches. Okay. See this one. The Boolean function y equals to ab plus cd is to be realized using only two input NAND gates. The minimum number of gates required is. So how many gates can we realize AB plus CD using two input NAND gates? So let us see this. How would you realize AP plus CD is m NAND gates, right? So AB, CD. Then if you just so okay, let me just first write the outputs here. We have AB bar plus CD bar. Now you want at the output AB plus CD. So if I NAND them again, I will get that, right? The output here will be AB bar dot CD bar full bar, which is AB bar plus CD bar, which is AB plus CD. So the number of gates that you need is 1, 2, and 3. Okay. So next question. Identify the logical approach operation performed by the given circuits. So very simple question. What will be the answer for this? Right. This is AB bar, and this is just a NOT gate. This is AB. This gate effectively is, and here it is A bar, B bar. This is again not NAND gate, so it is A bar, B bar, whole bar, which is A plus B, OR gate. Answer is option A. The minimum number of two-input NAND gates required to implement a two-input XOR gate is. Right. So if you need to make XOR from NAND, what you need to do? And if the question was XOR from NOR, then how many NOR gates would we need? Can anyone answer this? Right, 5. The architecture is exactly same, just add another NOR gate at the end. So to save time, always remember if you want to make from NAND NOR, if you want to make, sorry, just make it in the next page. NAND implementation, NOR implementation. You want to make, let's say, and not and or and not XOR as not. How many gates do you need for each one? For not, you need only one in both. For and, you need two in NAND and three in NOR. Three and two is one. For NAND, do you need how many gates do we need to make NAND gate from NOR gate? unit 4. Similarly, unit 4 here and 1 here. I need to set 3 into unit 4 actually, right? If you see, it is effectively AND gate plus one more or a not. Okay. XOR with NAND you need 4, here you need 5, here you need 5, you need 4. Yakub, is there a question? Okay, so if you see there is a pattern, right? If you ignore the first one, there is always this interchange here. So it would be better just remember for one, and for the other one you can already write by just interchanging. Is there any doubt in this? So it is important you remember this. So it is very much easier when you're giving some competitive exam like GATE. So if you remember this instead of trying to make it there and then, it is very easy to solve questions if you remember this table. Uh, is there any doubt? Do like any doubt like why 4 are required, why 5 are required, or the table is clear to all? Okay, so let's move on then to the next question. The logic circuit shown in the figure below can be minimized to. Please attempt this. So this is NOR gate. If there is any confusion, we have a bubble here. NOR, not, again NOR. What would be the output here? Then only you can answer. So this is going to be Y, let's say F. Beneath this is D. So let us see. So the circuit that we have is, I just read out the normal. Okay, so your input here is X and Y bar, right? Due to this bubble. When this bubble is there in the input, that means your input is inverted. So input going into the gate is Y bar, not Y. So this is the important thing to note here. So you have NOR of X and Y bar. So it will be X plus Y bar whole bar, right? Here. Here it is X bar and again NOR here. So it will be X bar plus sorry, X plus Y bar and whole bar. This is the NOR operation. To solve this, the X dot X plus Y bar. Let me do it step by step. So if I apply De Morgan's, it will be X bar dot X plus Y bar. This is the De Morgan. So if I remove these bars, it is X dot X plus Y bar. And if I just multiply simply, X plus X Y bar, take X common, 1 plus Y bar is X. So your output F is nothing but X. So this can be replaced by just simply the buffer. This means nothing, no change. So the answer is option D. Okay, I hope this is clear. Okay, next question. The maximum noise voltage that may appear at the input of a logic gate without changing the logic state of its output is termed as. So critical question. So I'll just tell the answer. Answer is noise immunity. So if you see, I think the first video, it will be clear in that. Now this question where we will use those uh, concepts that we studied about the hazards. What kind of hazard occurs when the Boolean expression of the circuit Y is this? Please try to see how to do this. Okay, so before solving this, let us see the theory part a little. So if you remember in one of the videos, was talked about how we can identify hazards from K-map, right? So a hazard may occur when two adjacent ones are not in the same group. Then it may cause a hazard, right? So this condition may cause a hazard. Here, if you see, these are two adjacent ones. They are in the same group. Here are two adjacent ones. They are in the same group. Two adjacent ones in same group. Two adjacent ones in same group. But these two adjacent ones are not in the same group, right? So this can cause a hazard. So basically, what is happening here? You see, D and D bar. This difference is there. So rest all is same, right? This is A bar B here. C is also same. Just D and D bar are changing. So when changing from D to D bar, it may happen that, like what we studied, right? Due to delays, D and D bar we are doing some operation. It may happen that due to the delays present, if this is D is this is D bar. Here, this period of time can cause some hazard. So whenever there are adjacent ones in K-map, it can cause a hazard, which are not if not grouped together. So what we can do to solve this question is we make it K-map and check the adjacent ones. So four variable K-map. Now you have to fill the ones. You have A bar, C bar, D bar. This A bar, this C bar, D bar. So it will be one and one here. Then you have B, C bar, D bar. You have B here. So B is here and C bar, D bar is here. So it will be one. Then you have A bar, C, D. This is A bar, This is CD. See this. Now we have BCD. This is B. This is CD. So we have one here. Okay. Now if we group them, then how we will group it? This and this and this. Right. Now if you see, are there any adjacent ones which are not in the same group? Are any adjacent ones, this is important, adjacent, not in same group? No, right? No. So you will not have any hazard. This expression will not give you any hazard. Whereas if you had something instead of this, let's say it was here, somewhere like some shift, then it would have caused a hazard.
Sir,
Yes.
by using this KMAT, how we can identify this as a static 0, 1 or dynamic hazard?
Okay, that is good question. So you cannot directly tell it. For that, we will see how to do it in the next question.
Okay, sir.
Yeah. So with KMAP, we can only see if there is a hazard or not hazard. Now, what kind of hazard will be there that we need to evaluate. Okay, so this question is this clear? All right. So again, when you have to find, just find if there is a hazard or not. You make a KMAP and see. Okay. So next question says, what is the hazard-free implementation of FABCD equals to this? So what we need to do, we make a KMAP is for making a hazard-free implementation. Step one is make KMAP. Two is you ensure no or all adjacent ones are in same group. You ensure this, right? Okay, first attempt this, then we will see. Okay, is anyone close to any answer? Please keep attempting. I'll just make the K-map till then we will see how to solve it. Meanwhile, okay, someone got C. If anyone else is getting any other answers also, please feel free to comment. We have one set 0, 2, 5, 6, 7, 8, 9, 12, 13, and 15. Okay, so if we have to make groups, let's see. So the first group that I see is this one. This group is B and uh, D. Right? It is BD. Then we can make another group. Let's just make only essential groups first. So we can have a group, another big group here. These four. This group is A C bar. Right? This is A. This is C bar. Intersection is A C bar. Then another group we can have is this. Right? So this is plus A bar C D bar. Right? And one more, this one is left. So we can group it either with this or we can either group with this. So let us group it somewhere and group it here. So this group is plus A bar B bar D bar. Okay. Now let us see the hazard conditions. Now we have all the ones in a group. Now let us see if all the adjacent ones are in same group or not. So we see one hazard condition is here. These two adjacent ones are not in same group, right? So we need to make sure these are in same group. So we will make another group here. Make a group. So red. So this group will become A bar B C, right? This we have made an additional group to avoid hazard. Now we have one more such case, right? This one and this one, these are adjacent, right? Like these and these two are adjacent. Similarly, this and this are also adjacent. So we need a redundant group here also. So let us make it with some other color, maybe dark blue, this one and this one. So this I can write as plus B bar, C bar, D bar, right? So we have choose. Now, if you see, now in all the groups, there is no one now which are not in the same group. If you see, there are no adjacent ones left which are not in the same group. These are in 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 same group. 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 All the adjacent ones have been taken care of. What about ABC bar? ABC bar is this. These are already in the same group, right? In this yellow group, these are already in the same group. Is it clear, Shatika? We have taken care of all the adjacent ones. So this is our SOP implementation with this hazard free. So which option does it match? We have BD, we have BD in these two options. AC bar in both the options. A bar, CD bar. A bar, CD bar is in both the options. A bar, B bar, D is in both the options. B, C bar, D bar is in both the options. A bar, B, C. Okay, this is A bar, B, C. So this is the correct one, D. Neetu, you are getting C. Is it clear? Where were you making some mistake?
So this not to avoid this hazard,
Yeah.
we doesn't group this one this 7 and 6.
Yes.
Uh, then that value is taken.
It is A bar B. This whole row is A bar B, and
Mm,
this is C, right? C and C both
yes,
are common. So it is A
A
bar
bar
B C,
B C.
not A B C.
That sorry, repeat.
Yeah. I was just saying in C and D options, only these, this is the different term, right?
Yes, yes.
So we have A bar B C, this, not A B C. A B C is not there. A B C would have been this, right? But we do not have this. We have A bar B C.
Yes.
So option D is correct. Is this clear to all? If there is any doubt, please ask.
Sir, actually, this 7 and 6 group is not needed. Is
Definitely,
it?
you are correct. Yeah. The only groups which were needed were these ones, right?
Yes.
Then took these two redundant groups to avoid the hazard condition. If it was like as just the minimize expression and not the hazard free, then this would have been sufficient. But it asks for
Mm.
hazard free also. So we need to make sure that all adjacent ones are in same group.
Okay, okay, okay.
Right?
Understood, sir.
These are definitely redundant, but just to ensure the hazard condition, we included them. Is there any other doubt? Okay, if not, let us move on. I have one more question, which is also based on hazards. Now, this was the question I think one of you were asking, maybe Neetu only. How do we identify which type of hazards are there? Right? We have this expression. First, we need to tell which type of hazard they may be susceptible to. One more after this. Yeah. So, for this question, how do we solve it? So, first you need to remember is hazard will be there if, like, you can see directly like hazard, the possibility of hazard will be there if you can either draw the k-map, or there can be a chance of hazard if there are a variable and variable bar in the expression. So here we see in this expression we have, there is a, there is no a bar, there is b, there is no b bar, there is d, there is no d bar, but we have c bar and c. The c bar and c may cause a hazard. Now, if you remember, we have three kinds of hazards: static, 0, static 1, and dynamic. Now, if we just go back once to that we learned here. Uh, sorry, right. Static 0 hazard will be in the case when we have a bar in the expression. Static 1 hazard will be there when we have a plus a bar in the expression. And dynamic hazard will be there when we have a bar plus a in the expression. So I will take this information back here. Static 0 hazard will be there when we have, since we are dealing with C and C bar, static 0 will be C and C bar. When C plus C bar, dynamic will be C C bar plus C. Okay, you can write this intuitively also, right? C C bar should always be 0. But hazard means like when this is the case, but you are instead of 0, you are getting some 1. This is static 0. Static 1, C plus C bar will always be 1, ideally. So it should have ideally been 1, but due to some delay between these two, you can get a 0 in the middle. Dynamic is the combination, so it is just some combination of these two. So now, to find out which type of hazards this expression might be susceptible to, we need to see in all the conditions of A, B, C, and D, 0, 0, 0, 0 till 1, 1, 1, 1. Do we get these cases or not? So can anyone tell me when?
Yes.
Yeah, is there a doubt? Neetu, are you saying something?
No, sir.
Yeah.
I
Okay.
answer your question.
Yeah. So in what condition of A, B, and D can we get this C C bar from here? What should be A equals to what, B equals to what, and D equals to what to get this? Let's call it F, to get from F, for F to change from this to C C bar. It's simple, right? A plus C bar, yeah, B plus C plus CD. You want to multiply these two, right? So if you just take A equal to 0, B equal to 0, D equals to 0, this expression will reduce to, so 0 plus C bar, 0 plus C plus 0. Just C bar. Is this clear? So when A equals to 0, B equals to 0, D equals to 0, you will have static zero hazard. Either side A equal to 1, B equal to 0, D equal to 1. Okay, so let us see this. You have A plus C bar, B plus C plus CD. If A equals to 1, 1 plus C bar, B equals to 1, 1 plus C, sorry, B equals to 0, 0 plus C plus D equals to 1, C dot 1. You will have 1 into C plus C. This is simply C. So okay, this is incorrect. A equals to 1, B equals to 0, D equals to 1 is incorrect. This is not causing any hazard. Okay. So now for static 1 hazard, you need C plus C bar. So in what condition of A, B and C, A, B and D, sorry, can we get C plus C bar from here? Okay, so let us try this. You have A plus C bar, B plus C plus CD. What you want is C plus C bar, right? So I see I have this C here, I have C bar here, I have this plus also. Somehow I want to remove this part and D. So D should definitely be 1. A should always be 0 to retain this C bar. This is plus. And we do not want this part. So if B is 1, this whole part will become 1. So if we have A equals to 0, B equals to 1, and D equals to 1, then it will be 0 plus C bar, 1 plus C plus C into 1. So we have C bar dot 1 plus C, just C bar plus C. Right, option is correct. A0, B1, D1. So in this case, we are getting this C bar plus C. So we have A equals to 0, B equals to 1, and D equals to 1. Right? So we have static 0, static 1 hazard, both are here. For dynamic, we need C bar plus C. Now how do we get this? To say 001. So let us try 001. We have A plus C bar, B plus C, CD, and 0, 0, and 1. A equals to 0, b equals to 0, b equals to 1, 0 plus c bar, 0 plus c plus c into 1. This is c bar plus c. Correct, right? So answer should be 0, 0, 1. Harsha says 0, 1, 1, 1. Let's see 1, 1, 1. A plus c bar, b plus c plus cd. If we have 1, 1, 1, this is 1, this is 1, this is 1. This will become 1 plus c bar, 1 plus c, d. Sorry, uh, c dot 1. So it will become 1 dot 1 plus c. That will simply be c. This is not right. This is correct. Harsha, is it clear why 1, 1, 1 is not the case? Okay. So now we have seen with some combinations of A, B, and D, we can get all three hazards in this expression, right? So this expression has static 0, static 1, and dynamic. All three hazards are possible in this answer. So answer is option D, right? So whenever you get these kind of questions, you just see which variables are there with given with complement, then check which conditions can you get these kind of expressions. Then you can answer them. Is this question clear? All right. We have one more question. So we have the same question as above. We know it has static and dynamic all the hazards. Now we have to give the hazard tree implementation. So how do we do this? One form is you make K-map, or maybe just like simplify this first, then make K-map, and then ensure adjacent ones are in same row. Okay, this is probably the attempt you should always give, but I will take I will show you another method. So this one you can try yourself, this method. I will show you another method how we can do this. Since we have did all this analysis here, this analysis can help us to directly give answer without doing the K-map. So let us see how do we do this, right? So if you see, uh, we had, let's talk about the static one hazard. We had our expression A plus C bar, B plus C plus CD. And if you remember, static one hazard was for condition, this condition, right? C plus C bar will come when A equals to 0, B equals to 1, and D equals to 1, right? In this condition. So when this condition came when we had A equals to 0, B equals to 1, and D equals to 1. So let's say I just want to remove the static 1 hazard. Then what should I do? Right? Ideally, what static 1 hazard is? Due to this C bar plus C, your output should always be should have been 0, but you are getting somewhere you are getting this 0, right? So what you can do is I write it like this: A plus C bar B plus C plus CD. This I already have. If I add an additional term, let's say plus A bar B D, right? This is A bar B and D. If I change this 0 and 1 to this form. So whenever this condition comes, A equals to 0, B equals to 1, D equals to 1, this term will become 1. This A bar B D will become 1. So your essentially your function would be C plus C bar plus 1, right? If I have this, then you will always have a static one. The zero case will not come, right? So by adding this term, we can avoid this static one hazard. Is it clear? We already identified where the static one hazard will come. Now we just change it into some term so that we can just ensure add that term and ensure that this hazard never comes. Similarly, we can do for static zero hazard. Static zero hazard we have already. This changes to C C bar when, let's say, A equals to B equals to B equals to what was it? Static 0 was there when with A0, B0 and D0. 0, B0 and D0. So write this. So what is static 0 hazard? You should have had 0, but due to this C C bar, you get a 1. So we need some combinational form of this to ensure whenever this condition comes, it still remains 0. It is exactly opposite of this condition. We need it to be whenever this C plus C bar comes, we need to add 1 in some way that it remains 1. Now if C plus C bar is 0, we need to multiply it with 0, right? To ensure it remains 0. So what we will do here, we will take this whole expression A plus C bar B plus C plus CD. Then we multiply it with some function, so simply A B, sorry, A plus B plus A plus B plus D. So whenever A, B and D, all three are 0, this whole function will be multiplied to 0. This will reduce to C C bar, and the C C bar into 0 will give you 0. So we will have a constant 0. We'll avoid this, right? So this is what you need to multiply to remove the static 0 hazard. Is this clear?
Sir, if we add A bar, B bar, D bar, then
Right. So let's say if I did not do this, A plus C bar, B plus C plus CD, and I add A bar, B bar, D bar. Now whenever these three will be 0, this term will become what? 1, right? This term will, we have a C C bar whenever A0, B0, D0 comes. So effectively you have C C bar plus 1 equals to, will give you 1, but you are trying to eliminate static 0 hazard, right? Your answer should have been 0, not 1. But this is giving you a 1 again. So this will not remove your. We need to do something to make this term 0. So we need to multiply it with z.
So always for static zero hazard, we use POS form of that.
Definitely. Okay. This is
Okay.
POS form.
For static one, it is SOP form.
Alright. It is very good deduction. So this is we use POS for this. You use SOP because it is just the nature of the hazard itself, right? It should have been 0. We want to ensure it to remain 0. That's why we'll multiply it by the condition so that it remains 0. Here we wanted it to be 1. So we'll add something that becomes 1 when this condition arrives. So it remains 1, does not go to 0. So these both are clear, right? So till now, to remove these two, your expression has become a plus c bar. This is not there. We remove this. C bar. B plus c plus cd. A bar, b bar, d bar. Sorry, we did not add a bar, b bar, d bar. We did multiply it with a plus b plus d, and we added a bar bd, where this we added for static 0, this we choose for static 1. Correct? Till now, is it clear?
Yes, sir.
Correct. Now we have one more hazard to take care of, right? The dynamic hazard. So let us see that also. Third case is dynamic. For this, we have c bar plus c. Your expression, I'll write it again, a plus c bar, b plus c plus cd. Your expression, and you have the dynamic hazard when a, b, c is 0, sorry, to be 0, 1, 1, right? If I remember correctly. Check. Sorry, it is 0, 0, 1. So let us do 0, 0, 1. Okay. So, mm, so let me write the expression that we already have. We have a plus c bar, b plus c plus cd. Then we added plus a bar bd, and we multiplied with a plus b plus d. Right now, our condition is a0, b0, and d1. We need to avoid this. So here also we do the same thing as we did for static 0. Uh, what we can do is a plus b plus d bar is famous term. If we multiply this, then let's see what we will get. Multiply it here, a plus b plus d bar. Okay, so Okay, so this hazard actually a dynamic hazard, right? So it will depend on the condition of C. Let's say if C equals to 0, so it will be this actually is always 0. This will become 0. This should be this changes into uh, your output should be basically 0. So this changes into static 0. Or if C equals to 1, this changes to static 1. Okay, so by multiplying this, what we are doing A0, B0, D1. So we multiplied this whole thing by 0. And we can also add plus A plus B. We cannot do that. Okay, so just forget this for a moment. So we have, let me see it again. We have C, C bar plus C. This is the condition when we get a dynamic result. So here if C equals to 0, this should always be 0 anyways, and the C will become 0. So you should have get static 0. Your output should be 0, should remain 0, and C equals to 1. Your output should remain 1. So your condition is A equals to 0, B equals to 0, D equals to 1. Then when this is the case, you are getting C, C bar plus C. So you need to add or multiply something to get correct result. So what you can do is multiply, add first, and C equals to 1 plus A bar, B bar, C, D, and multiply by A bar, B bar, C, D, and multiplying by A plus B plus C bar plus C plus D bar. Now this will remove the dynamic hazard, right? What I've done here is when C, let's say when C is 0, basically we need to either do SOP or POS, right? This we have seen till now from static 0 and static 1. Now C, C bar plus C. Output when C equals to 0, we should get 0. So to get that 0, we multiplied this POS form A plus B plus C plus D bar, where when C equals to 0, you will get the whole term to be 0. Here also this, since we have the C here, it will become 0. So when C, if this is your new f, when C equals to 0, your f equals to 0. When C equals to 1, when C equals to 1, this whole term will become 1. This whole term will also become 1. So you will get your f will become 1. So multiplying these two things solves our problem. Is it clear? The dynamic result. We need to multiply this term and add this term. Uh, is there anyone? Harsha, Sahatika, is this clear? Okay. So now our final expression, let us write. It was we have added, multiplied another term, a plus b plus c plus d bar, added another term, a bar b bar c d. Now this expression has become hazard free. This removes static 0, this removes static 1, these two remove dynamic. You can do some reductions here also. You take these two terms, a bar b d plus a bar b bar c d. Take a bar d common, get b plus b bar c, which is b plus c, right? So a bar b plus c d. And here in these two terms, you do a plus b common, we have remainder c plus d bar and d. To multiply this, a plus b c d plus d d bar. You know, you get a plus b c d. So your expression can be a plus b c d, a plus c bar, b plus c plus c d plus a bar b, b plus c. This can be your final answer. Is it
So
wrong?
can you repeat this dynamic? I lost the connection. So.
Sorry.
Can you repeat this dynamic?
Yeah, sure. So Hatika says, is it wrong to multiply a, b, d bar since c equals to 0? Uh, Actually, yeah, you are correct. You can multiply a, b, d bar. So that will simplify things. Here also we can remove this. So your final expression will become something like this. Uh, I will resolve this, don't worry. I'll just trying to see what we are getting. We need to remove this. let us do the dynamic part again. Okay, so what we discussed in dynamic part was we have this expression where in under this condition we get this C plus C bar plus C, which gives us some dynamic issue, right? And this was our solutions to static 0 and static 1. Now if we analyze this C bar plus C, when C should be 0, we should always get 0 low. When C should be high, we should always get high. So we need to add some conditions in this so that, like, we need to either do SOP or POS so that we ensure this happens. When C equals to 0, it remains 0, and C equals to 1, it remains 1. So what we can do is we can multiply A plus B plus D bar here. Like this. So let us do both. You add, you multiply the SOP POS form and you add the SOP form. Right now, let's see when C equals to 0. When C equals to 0, is this F becoming 0? This will multiply by 0, but here this will give you a 1. All right. Uh, when C equals to 1, this will give you a 0. So you need to have C here. Right now, if you see, if we multiply this and we add this, when C equals to 0, F becomes 0. When C equals to 0, these will multiply to be 0, and this C equals to 0, you will get F equals to 0. When C equals to 1, this will become 1. If this is multiplied to be 0, it does not matter. You will get 1. F equals to 1. Uh, is it clear now? So we need to multiply this and add this to make it uh, actually we cannot do this because if you see in a K-map what it will do, This will be an isolated one, right? We are not grouping it with anything. So this operation we cannot do. We only can only do three variable operations. So, okay, so if I remove this, then if I see if c equals to 1, then what will happen? And c equals to 1, this will go to 0. We will still get f equals to 0. Okay, I think I'm doing something incorrect here. So for dynamic, I need to see this is not correct. So maybe I'll revisit this and come back to you. What you can do is, uh, okay, KMF concept. What I said was what I was also doing is I was adding a plus what I was doing a bar b bar c d. I was asking if you do this, then this condition will become fine if I add this. Now the problem with this is how do we remove these hazards? We saw that there are isolated like 1, 1, 1, 1. We group them together. But by introducing this term in a four variable K-map, what it will do, it is like an isolated one. This we are not grouping anything here. We are actually introducing another isolated one. So this is something we should not do, right? That's what I was saying. So that's why I'm a little bit skeptical, like we should do this or not. So what you guys can do is for static zero and static one we have seen. For dynamic, uh, what you guys do is just make the K map and do this expression and uh, just form the group so that no adjacent ones are left ungrouped, and then see what you are getting. So the total expression, whatever is left in this, we will get the answer is that. So the answer that I have actually also does not consider this. It only considers this part till here. But then I'm not sure about this f equals to 1 condition. So, but if this is satisfied, if this satisfies the condition and we, but just by doing this, we do not get any ungrouped one, then that means it is correct. It must be correct. So we can conclude that the K-map is the way to go. But okay, so if we see the options, what we have done is multiplied ABD, added A bar BD. So A bar BD is multiplied. What is the A plus C bar? Right. So this could be the answer because what we did was plus A bar BD and we multiplied A plus B plus D and A plus B plus D bar. These two can be reduced to simply A plus B. So this could be the answer, but verify it with Kenan. This is, I think, the ultimate thing that will solve. So anyways, so this gives us like conceptually, it gives us some idea like when static one is there, we need, why do we need POS form? Because if we add this condition, we will bypass this condition. Similarly, in SOP, if we multiply this, we will always ensure it to be 0. For dynamic, it is little bit difficult to analyze here, as we have seen. So for that, let's just stick to K-max. So I think the answer should be 1. For dynamic, we get this condition. One of this condition is this. So if we multiply this static 0 and dynamic 1, we get A plus B. And this is just simply static 0 condition. Okay. So is there anything anybody wants to ask?
Sir, any tips to solve this expression by using NAND or NOR gate? Very means
Solve.
if we get an expression, solve
Right.
it using NAND or NOR gate.
You mean realize how many number of gates you are required? Some those kind of
Uh,
questions.
no, no. In theory exams, we have to solve this expression by using NAND or NOR gate like that.
Like I do not get the question. What does it mean to solve it using random?
Sir, if a function f is equal to b bar plus c,
Okay.
then solve it using NAND gate and NOR gate like
Let's
that. Any
f equals to b bar plus c. Now,
yes.
first of all, what do you mean by solve? It is already minimized.
Using NAND or NOR gate, can you?
Do you even want me to make this circuit using NAND and NOR, right?
Yes, yes,
Okay.
yes.
So I think it is okay. When you see a NAND expression, right? So let us go from behind. Uh, let's take first NAND and we'll take NOR. The ref is B bar plus C. So you convert it somehow that you get some NAND formulation. Sorry, NOR formulation. Sorry, NAND formulation. NAND formulation always something into something bar, right? So what should I do here so that I get this? So I can have this C bar, I can have this B. If I do this, I will get B bar plus C, right? This is what I want. So to make it using NAND gate, what I can do is I have a NAND gate. I'm getting here B C bar whole bar, which is B bar plus C. I'm giving input B. Now it's up to you. C bar can you give or not? If you cannot give C bar, add another NAND gate and give C. Now this is B C bar, then NAND of B C bar, which is B bar plus C. Is it clear?
Yes, yes, sir. And for NOR gate,
Yeah. For NOR gate, again you have F equals to B bar plus C. Now what is the NOR implementation? Something plus something whole bar, right? So what can we have? We already have a plus. So what we can do is for NOR B bar plus C, I do this bar 2 times, right? So uh, then I can solve it as B bar dot C whole bar Or let us do a simple thing. Let's see, this is an OR get implementation. B bar plus C. Let's say if I had B, C, and B bar plus C at another NOR. Sorry, I get B plus C bar, another NOR, I get B bar, B plus C. Now instead of B, if I give B bar, B, B bar, it will be B bar plus C and it will be this. I think this is the NOR implementation. So how you should approach this, if your function is given like in, let's say, you have to do NAND abstraction, right? And NAND, you see like it is like multiplication and kind of operation. So you like backtrack. You start from the back. You see how you will convert this into this NAND form to get the answer, right? Now, once you have converted this, then you can simply make the NAND gate and do it. Whereas in NOR, so this expression is already in like the sum form, right? Which is the OR operation. So just simply do an OR and do a NOT out of it.
Yes,
Let's
sir.
say if it was B bar C, then it would become difficult how to do it with NOR. Then again, you need to do backtracking. How do you implement B bar C with NOR? Then you need to see. NOR is again, now you can do this, right? Which is B bar C. Now what will give me this? B plus C bar, right? So the NOR operation will be B C bar. So we need B plus C bar whole bar. C bar we can replace with this. Now this is similar to what we had done for the NAND operation there. So just see what you are trying to implement, then I think it will be easier. Yeah. Is this clear?
Yes, sir.
Okay. Is there anything else? If not, we can close the session. Okay. So just try to do this question again with KMAP once and see if you are getting the same answer or not. Okay. If there is some issue, we will discuss it in the next class. Thank you everyone for joining this live. See you next week.